All right, today we're jumping right into the very heart of how databases actually work. We're going to explore the fundamental structures that power pretty much every single app you use. So get ready for a tale of two trees.
Just think about that for a second. You search for a product, you load a social media profile, you check your bank account, and somehow a database finds that one specific piece of information from a sea of billions, and it does it, almost instantly. How on earth is that even possible?
Well, the magic all happens right here, deep inside the system's architecture, in a component called the storage engine. This is the unsung hero, the powerhouse that's responsible for the incredibly complex job of actually storing, retrieving, and managing data. It makes everything else possible.
But every single storage engine, I don't care how it's designed, has to face this one huge, unavoidable problem. It's a fundamental law of physics, really, and it shapes every single decision that follows.
And this right here is the absolute key. Memory is blazing fast, but disk is just painfully slow in comparison. So the single biggest performance bottleneck for any database is having to read from or write to a disk. The name of the game, the entire game, is to minimize the number of times you have to touch that disk. So how do you solve a problem like that? Well, let's meet our first champion in this story, the classic answer. A data structure engineered specifically for this slow world of disk storage. It's called the B-tree.
The genius of a B-tree is all in its shape. Instead of being tall and skinny, it's short and very, very wide. This width, what we call a high fan-out, means that every single node can point to tons of other nodes. Think of it like the most efficient library card catalog you've ever seen. In just a few lookups, you can go from millions of options down to the exact one you need.
So when you need to read something, it's incredibly efficient. You start at the top, at the single root node, you make a choice, and you hop to the next level. Because the tree is so short, you just repeat this a few times, and boom, you've landed on the exact page on disk that holds your data. You've minimized those slow disk reads.
And this is why B-trees are the undisputed kings for what we call OLTP, or Online Transaction Processing Systems. Think about any app where you need to fetch specific records fast. E-commerce sites, banking systems, social networks. They're all about quick, targeted reads.
Okay, so if B-trees are so amazing, why would we ever use anything else? What's the catch? Well, it turns out their greatest strength, that perfectly organized structure, actually becomes a bit of a liability when you need to write or update data. This is where the B-tree's design kind of bites it. See, it does updates in place. So to change even one tiny little byte of data, the database has to first read an entire page, a whole block of data, from that slow disk into memory. Then it makes the tiny change, and then it has to write the entire page back to the disk. That whole process is called write amplification, and it's a crazy expensive operation. A real performance killer if you're doing a lot of writes.
So all that overhead for writing, that created an opening for a new contender. A completely different approach, built from the ground up for one thing and one thing only. Just absolutely blazing fast write performance. So let's talk about the log-structured merge tree, or LSM tree.
The philosophy here is just completely different. It's radical, really. An LSM tree never modifies data that's already been written. Instead, it treats the database like a diary or a log. New data comes in, just tack it on to the end. That's it. All writes, all updates, even deletes, they're just new entries written one after another.
So, a write becomes this super simple two-step dance. First, the data gets written into a sorted table in super fast memory. We call it a mem table. Then, once that mem table gets full, the whole thing gets flushed down to a brand new permanent file on disk. It's all fast, sequential writing, exactly what disks are good at.
And you can probably see where this is going. This makes LSM trees the perfect choice for any system that's just getting slammed with a fire hose of new data. We're talking event logging, time series data, analytics platforms, anywhere write speed is the most important thing.
But, in engineering, there's no such thing as a free lunch, ever. The LSM tree's incredible write speed, it comes at a price, and this is where our two champions really go head-to-head.
It's the natural question, right? If writing is so much faster, what's the downside? Why not just use LSM trees for everything? Well, the catch comes when you need to read that data back. And here it is, the fundamental trade-off laid bare. B-trees pay the price on the way in with write amplification, but LSM trees, they pay their price on the way out with something called read amplification.
Okay, so think about this.
To find the latest version of just one piece of data, a read operation has to do a whole lot of work. First, it's got to check that in-memory mem table. If it's not there, okay, now it has to go searching through all those different sorted files on disk, from the newest to the oldest, because an updated version could be in any one of them. This whole process of checking a bunch of different places, that's read amplification. And it means that simple reads can be way more complicated and potentially slower than in a B tree.
So, which one's better? The read-optimized B tree or the write-optimized LSM tree? The answer, of course, is it depends. It completely depends on what you're trying to build.
This table right here is pretty much the ultimate cheat sheet. If your app is all about fast, targeted lookups, like an e-commerce store, you're probably going to want a B-tree. But if you're ingesting huge volumes of data, like for an analytics platform, an LSM tree is your friend. It's all about picking the right tool for the right job.
This quote really just nails it, doesn't it? If there was one perfect, magical storage engine that was the best for every single situation, well, everyone would just use that one and we wouldn't even be having this conversation. This is what engineering is all about, making smart, deliberate trade-offs.
So that's really the key takeaway. The next time you use any app, just for a second, ask yourself, is the database behind this thing a meticulous librarian carefully filing everything away for super fast retrieval? Or is it more like a rapid-fire diarist just scrambling to write everything down as fast as it happens? If you can answer that, you're starting to understand the very heart of the database.